Hey guys, this is Coach Lowe, and we're going to talk a little geometry here. We are in Chapter 8, Section 2, and this is the Pythagorean theorem and its converse. Pythagorean theorem and its converse. All right, so let's get started. We've worked with the Pythagorean theorem quite a bit, and so in this lesson, we're going to look at the Pythagorean theorem, and of course its converse, so switching it around, remember the if and only if, so we can have this statement and then its converse where we switch the hypothesis and the conclusion, but we're also going to look at Pythagorean triples, so some common side lengths that we'll see over and over again in right triangles. And then we're also going to talk about a little EOI question that we looked at a couple of weeks ago, and I told you we would get to the point where we would kind of discuss that further, and today is the day. All right, so let's first write down Theorem 8.4, which is the Pythagorean theorem. And it says in a right triangle, so Pythagorean theorem starts out with a right triangle. So that's the first part. We have to have a right triangle. In a right triangle, the sum of the squares of the lengths of the legs is equal to the square of the length of the hypotenuse. The sum of the square of the lengths of the legs equals the square of the length of the hypotenuse. Now, if you want to write down what I said, then you can look up Pythagorean theorem in your book and write it down. That's totally fine. So in a right triangle, the sum, so there's the addition, of the squares of the lengths of the legs is equal to the square of the hypotenuse. Usually we write it like this: a squared plus b squared equals c squared. Or maybe you've seen it written c squared equals a squared plus b squared. Either way is correct. All right, so that is the Pythagorean theorem. All right. And this is where the right angle is C. The right angle could be any letter. We can rearrange the Pythagorean theorem, but the key is the hypotenuse is always on the side by itself. So it's the leg squared equal to the hypotenuse squared. And remember, the hypotenuse is the side that's opposite the 90-degree angle. It's the longest side. 90 degrees is the biggest angle. That's my hypotenuse. All right. So let's talk about Pythagorean triples. These are numbers that work in the Pythagorean theorem. If you plug them into c squared equals a squared plus b squared, these are actually whole numbers that work. There are decimal numbers, fractions, just any real number, not any real number, but there are real numbers that work in the Pythagorean theorem when you plug them in. But we are going to talk about common Pythagorean triples that you'll see throughout your math career. 3, 4, 5 is a common Pythagorean triple. So that means you can probably guess which numbers go on the sides and which numbers go on, or which number goes on the hypotenuse. So 3, 4, 5. Common Pythagorean triple. 3 squared plus 4 squared equals 5 squared. So if they ask you if these are lengths of a right triangle, you plug them into the Pythagorean theorem. 9 and 16 is 25. 25 equals 25. True. Now, you can also have multiples of these. In other words, I could multiply every side by 2, right? That would be a dilation, that would be an enlargement, and this would be 8, 6, and 10. So still a manipulation of a Pythagorean triple. In fact, I could do something like this and say, find the missing side length. Well, you could look here and see I've multiplied that by 3, I've multiplied that by 3, which would make this side 9. So different things, different questions they can ask you. And so as you look at those, the first thing you really want to do is say, hey, is this a breakdown or is this an enlargement of a Pythagorean triple? All right, so there's one. I'm going to give you about 4 of these. There are several in your book. So if you look up this section and want to write a few more down, you can. Another one is 5, 12, and 13. 13 being the hypotenuse. Another one 8, 15, and 17. And then a fourth one, 7, 24, 25. These are fairly common. And then as you move through here, I mean, you could put, um, from this point, we could make a lot out of these 4. In other words, I could multiply all these by 2. I could multiply all these by 2, by 2, by 2. Then I have an enlargement of that Pythagorean triple, enlargement of that specific right triangle. So as we move through here, we could say 3x, 4x, 5x, right? So I could plug any number in for x. I could have a multiple of this original Pythagorean triple. Same thing with each of these. All right, so if you wanted to make another right triangle that went along with this Pythagorean triple, but maybe was an enlargement or a reduction, then you could just plug in a value for x like a half and come up with another right triangle there. All right, so let me give you one and let's see, kind of like the one that we did right here with the red numbers, but let's try this one. Is this, or can we use a Pythagorean triple to find the value for x? All right, so I see these are both even, so maybe take a 2 out and let's see what these are. So 2 times 13 and 2 times 12. So look up here at these top 4. Do we have one that has a 12 and a 13? 13 is a hypotenuse. And we do, it's number 2. So that means this would be 2 times 5. So x is 10 using the Pythagorean triple 2, 12, excuse me, 5, 12, and 13. All sides have been multiplied by 2. All right, let's move on. The converse of the Pythagorean theorem, which by the way, we've kind of used this already. So this is theorem 8.5. The converse of the Pythagorean theorem says if you're looking at a triangle and the sum of the squares of the legs is equal to the square of the length of the hypotenuse, it's a right triangle. So we did this back first semester earlier in this book, and we talked about, hey, let's see if this is a right triangle. We plugged it in the Pythagorean theorem. If it worked, then yay, it's a right triangle. If it didn't, we said no. We're going to take that a little bit further today. All right, so let me go ahead and write this out. If the sum of the squares of the lengths of the legs of a triangle are equal to the square of the length of the hypotenuse, then the triangle is a right triangle. All right, so in other words, if a squared plus b squared equals c squared, then the triangle is a right triangle. All right, so now a reminder, the longest side, when you're checking these, the longest side goes here always. So they'll give you 3 numbers, stick the longest one over on the side by itself where the hypotenuse is supposed to go, because the hypotenuse is opposite the 90-degree angle, which will make it the longest side. There's not going to be an angle bigger than 90 degrees. Okay, if it's a right triangle. Now, here are the inequality theorems. Here's where we're going to bump it up a little bit. All right, so 8.6. If the squares of the lengths of the longest, if the square of the length of the longest side of the triangle is less than the sum of the squares of the lengths of the 2 sides, then the triangle is an acute triangle. So in other words, let me say this a different way. If c squared is smaller than a squared plus b squared, it's an acute triangle. And some of you guys, we kind of talked about this on the practice EOI stuff that we were looking at. But so when I do c squared equals a squared plus b squared, that's why you guys see me write it this way quite a bit. When I do this, if it's equal, it's a right triangle. If the hypotenuse is shorter than the sum of the squares, so if it's smaller, then it's an acute triangle. Guess what happens if it's bigger? Yep, it's an obtuse triangle. All right, so those are the two theorems, 8-6 inequality theorems, 8-6 and 8-7. All right, so let's try one, maybe a couple, and then we'll wrap it up from there. All right. So remember, if it's c squared equals a squared plus b squared, right triangle. If the hypotenuse is smaller than the sum of the sides, acute triangle. If the hypotenuse is larger than the sum of the legs, then it's obtuse. All right, so I'm going to keep those little notes right there. And let me give you some side links. This is not example 1, it's example 2. All right, so side links 10, 11, and 13. All right, so we are going to plug this into c squared. We don't know if it's equal or not, equals a squared plus b squared. This is a little check, right? So longest side is going here. So 13 squared equals, and it doesn't matter on the other two, 10 squared plus 11 squared, and we're trying to figure out if these are equal. So 169 equals possibly 100 plus 121. So perfect squares, 13 squared, those you should have memorized. If you don't, then work on them. 169 is equal to 221. Well, 169 is not equal to 221. 169 is actually less than 221. So the length of the side opposite the largest angle, or the longest side, is smaller than the sum of the other two sides, the sum of the squares of the other two sides. All right, so the longest side squared is smaller than the other two sides squared and then added together. So what kind of triangle is this? So we're back here. C squared is less than a squared plus b squared. So we have an acute triangle. All right, so if it works in the Pythagorean theorem, if we get equal, it's a right triangle. If we work it out in c squared, the side where you've just plugged in the longest side, if it's smaller than the sum of the squares of the other two sides, it's an acute triangle. If it's bigger, it's an obtuse triangle. All right, guys, that's all I have for you today. Talk to you soon. This is Coach Lowe, and I'm out.